How you doing? I'm Mr. Rose, and today we're going to be working out of a problem out of Chapter 4, number 57, from University Physics, Young and Freeman, the 13th edition. So hopefully you have a copy of this book around. Again, I'm not going to read you the entire problem. And like always, I always suggest you trying the problem before you watch me go out and solve it. It's much easier to watch me than for you to do it yourself. So again, if you don't have a copy of this book, Young and Freeman, University Physics, 13th edition, I'm sure there's a copy online for you to take a look at. Question 57, here we go. I've got two boxes, A and B, and they have a force that's applied 80 newtons up. Now, they tell me in the problem that this is actually why I picked it, because it's a little bit interesting. Even though I'm pulling with a force up, they told me box B is moving down with, moving down at 12 meters in 4 seconds. They defined for me the tension between A and B, 36 newtons, and they told me the whole object starts at rest, and they want me to find two parts, part A and part B. Part A is what is the mass of box B, and then part B is what is the mass on box A. So I'm going to figure out, I want to know what the mass of B is, and I want to know what is the mass of A. Now again, the reason I picked this is because Newton's laws, and for a long time after this, free body diagrams are the key to solving a ton of mechanics questions. This problem is a little bit different. Here we're applying a force up, but we're physically, or the person in the problem is not strong enough to lift this whole thing up, so it's accelerating down. The first thing I need to define is picking a coordinate system. Now this is totally up to you, and I have really two good options here. I'm going to define this in a standard XY coordinate system, meaning my up force is positive, and this is falling in a negative direction. You can do it the other way if you'd like, just if you do, make sure that our force is negative if you define down as a positive direction. That is going to be real key today and moving forward in physics. Next, with every free body diagram or Newton's laws problem, we definitely want to draw some free body diagrams. And I have two objects here. I've got object A and object B. So I need two free body diagrams. I need a free body diagram for A, a free body diagram for B. So I'm going to do A first. A is going to be a little bit more complicated, but I'm still going to do A first just because numerically that's what it is. So for free body diagram A, we always have, not always, but we almost always have two forces. In this case, we do. I've got a defined force up, F, and I know this is an object, so I definitely got a weight because we assume this thing is here on Earth. I've got a M, wrong color, I'm doing A. I've got a mass A times gravity going down. Now, if I look at that, well, that force I drew looks bigger than that force. Mr. Rose, isn't that wrong? Yes, that is wrong because there's a second force here. We've got another force, and I'm going to start to color code. That second force that is acting in the down direction is my tension. So I've got to add that to my diagram. There's a tension that's also going down. And those two forces combined have to be bigger than force F. How do I know it's bigger than force F? I know it's bigger because they told me that this whole object, something else we should include near our diagram, they told me this whole object is accelerating down. Now also I want to note, as I just thought of this, don't fall into this trap. They told me that my initial velocity was 0. They told me it's moving down 12 meters in 4 seconds. If you did quick math, 12 divided by 4, 3 meters per second. This guy's moving at 3 meters per second. It's not. By definition, it started at rest. It started to move, therefore it has an acceleration. So I can't just do simple average velocity to find out how fast it's going. It's not actually going that fast. Just want a glass of water. So here's my free body diagram for block A. My free body diagram for block B is much simpler. I only have two forces on this guy. I've got the rope here holding it up, which means I've got a tension. and I've got a force due to gravity, or an m times g, going down. MBG. That's it. And that's not the best diagram. This needs to be a little bit bigger, because we know, just like A, this sucker is accelerating down. Now, what do? I'm not stuck here yet. Oh, I want to give that an adjustment. There we go. I'm not stuck, but now I need to start to recognize what things are equal. Tension is tension. I have the tension of A on B. Newton's third law says forces come in pairs. Tension on B has to be the same thing. A on B has to be B on A, which means tension and tension are the same. These objects are connected. Accelerations and acceleration is the same. And I know at some point I want to apply Newton's law, F equals ma. So it's probably good to figure out what this acceleration is. How am I going to figure out what that acceleration is? With my given information, I know a lot of stuff. I know V naught is 0 meters per second. Remember, I can't fall into that trap of 12 divided by 12 divided by 4 for a final velocity. I don't know what the final velocity actually is. I do know, what else do I know? Oh, I know it moves down 12 meters in 4 seconds. So I don't know a velocity, but I know a y minus y naught is 12 meters. I know a time is 4 seconds. So now we can pull back into our kinematics bag of tricks, and I can say y minus y naught, v naught t plus 1/2 a t squared, where my initial velocity is 0. And I can say that acceleration is equal to 2 times y minus y naught divided by t squared. Now, I can leave this in variables, and I keep saying I like to leave things in variables, but here I actually want a number because it's going to get a little bit ugly here, and I don't know if we want all of these variables floating around. So my acceleration is going to be 2 times negative 12. Remember, I defined up as positive, so moving down has to be a negative. Oh, look at me, bad notation. It's got to be a negative 12. So 2 times negative 12 is negative 24. And I'm going to divide that by t squared. So by 4 squared is 16. And I get an acceleration negative 1.5 meters per second squared. Now that I have acceleration, it's going to be real easy for me to apply Newton's law. Where do I apply Newton's law to? I'm going to apply Newton's laws to object A and object B, because right now I've got 2 unknowns. I know if I have 2 unknowns, I need 2 equations to solve for 2 unknowns. So I'm going to, I'm going to build here, I guess. Newton's second law, F equals ma for free body diagram A, which means right now I don't care at all about free body diagram B. My forces, sum of my forces, I've got F. That's a positive. Minus, those are in my negative direction, minus a tension, minus ma, mass AG equals mass times acceleration. Still mass A times my acceleration. Put a partial box around that guy because I'm going to need it. Right? What don't I know here? Actually, the only thing I don't know is A. I could plug that sucker right in and solve now if I want to. For box B, I've got a tension. That's tension going up. Minus MBG minus MBG equals MB times A. So as I'm figuring this out, I actually didn't even need to do this step. I've got 2 equations. If I never solved A, I have 2 equations and 2 unknowns. Right? I know force, I know tension, I know gravity. If I didn't do this, I don't know acceleration. Here I know tension, I know mass, I know gravity, I don't know acceleration. I could have just solved one in terms of the other. Man, I could have just solved one in terms of the other, subbed in, and I still could have found MA and MB. So that was just not as elegant, obviously, but an alternate way to do it. In fact, I knew you could do that. I'm suggesting you go back and check it, see if it works out without acceleration. 2 equations and 2 unknowns. So from this point, actually, it should be pretty trivial. I guess let's just finish it out here. For object A, let's see, I'm going to bring that to the other side. So I'm going to say force minus tension is equal to, if I add the MA to the other side and then pull, I can factor it out, MA times the quantity, so I added that to the other side, pulled it out, A plus G, A plus G. And that should be my general, not done yet because I'm solving for M. MA is equal to my force minus my tension divided by A plus G. That should be my mass of A. We'll check things at the very end. My mass of B, which I have in this color. Mass of B looks like it's going to be easier. Let's see, I'm going to bring that to the other side. So I'm going to have... I can't hold on to these markers. For B, I've got tension equals MB, add that, A plus G, A plus G. All right, I brought that to the other side, A plus G. So my mass of B should just be equal to the tension divided by A plus G. Those are my general expressions. I'm going to leave you to plug in the numbers. That's all I have for you today. Let me just, here we go. Oh, didn't box that. That is all I have for you today on this problem. Solving for the mass of A and the mass of B. Now, when you plug these in, if you end up with a negative mass, that means you did something wrong. If you plug these in and we end up with a negative mass on my account, that means I may have messed up a sign as well. Fairly confident I didn't. That's all, again, I have for you today. Please feel free to like, click, and subscribe. Leave me a comment. If there are questions out of this text that you'd like me to solve, by all means, drop a comment, or if you happen to be on my class or in my classroom, feel free to send an email or drop a line on the Google Classroom. Thanks for watching. Hope you got it, and I'll see you next time.